In the last lecture, we discussed the reduction rules for the lambda calculus. These rules define when it's admissible to be able to rewrite or reduce some term to some other term. We talked about the three big reductions: alpha conversion, which allows us to rename variables; beta reduction, which is really the heart of computation but relies on substitution; and then eta reduction or expansion, which characterizes a notion of extensionality. Now in this lecture, we're going to talk about various reduction strategies. If you think about the reduction rules for the lambda calculus as defining a set of possible moves you might make at any one point of a game, you can think of a reduction strategy as being a sort of strategy you're taking and exploring that game, sort of telling the lambda calculus precisely which beta rule to apply at any one point. Let's look at some examples to see what I mean by that. So one observation that I want to make is think about how you might evaluate a lambda expression like this one right here. You've got this lambda xx, the identity function, applied to this application over here, where I've got lambda zz applied to y. So whenever I get to a reduction like this, I always have two choices. I could either sort of immediately perform the application and substitute the argument into the body right here, or I could continue to explore and reduce that body. Those are basically the two choices that I have, and I have that choice at every point where I have a lambda expression with a sort of beta redux or a lambda and function position, so I could potentially perform beta reduction. I'm going to assume a few basic but important choices that are not really inherent to the lambda calculus, but something that's going to allow it to make it a lot easier to define computation. So first, we're going to assume that terms are sort of evaluated top-down. What I mean by that is that when we try to work on a piece of computation, we're going to look at the term sort of from the outward in, and we're going to determine what to evaluate by making some decision by looking at that sort of hierarchy. The next one is that we never evaluate under a lambda, and so we don't actually evaluate functions until they are actually applied. So let's look at this example right here. I've got lambda x, and then under the lambda, I've got the omega combinator. All right, so I know from the last few lectures, if I start beta reducing this expression, there's no end in sight. I could continue to beta reduce this all day, and it would never terminate. It's just the simplest looping combinator you can get. However, in pretty much every programming language, this expression is in what's called weak head normal form. And in weak head normal form, this means something is a sort of lambda. It's fully evaluated to a value. Well, in weak head normal form, it doesn't matter what's under the lambda because we're never going to actually continue to evaluate that lambda until someone actually applies a function. Whenever you construct a lambda, you never actually evaluate that function until it's applied, in the same way that you don't evaluate the else branch of an if until you check the guard. Now, in defining our reduction strategy, we essentially have two choices. And these two choices are usually what's called call by value and call by name. In call by value, we always reduce arguments to values before we apply functions. In call by name, we always apply functions whenever we can without having to worry or lazily evaluating arguments. So in call by value, we're performing the most amount of computation we possibly could, in the sense that whenever we have an opportunity for beta reduction, we always force ourselves to have to evaluate these arguments. This is going to lead to some expressions not terminating when we use this call by value interpretation that would terminate under the call by name interpretation, as we'll see in a few slides. All right, so I'd like to just give a concrete example to sort of demonstrate what I mean when I say that whenever you get to some application, you always have some choice of possible beta reductions to apply. Now you might wonder to yourself why it makes sense to allow us to have multiple different beta reduxes for a term. So we have these terms and we can evaluate them using different kinds of reduction strategies. That seems kind of weird compared to most of the times when we write programs where we expect them to have only a single answer. So back when they were starting to study the properties of the lambda calculus, people figured out that this certain property holds, which is called the diamond property. What this property says, it's more formally known as the Church-Rosser property of the lambda calculus, is just that if you have some expression e that you start from, and you imagine rewriting or reducing that expression down to some expression e0, Now imagine you started from E and you also, using some other sequence of rewrites, not necessarily the same one, you also get to E1, which is maybe a distinct term. So you can get to both E0 and E1, but from kind of different directions. Well, the Church-Rosser theorem says both of those terms will eventually reduce to, or can eventually reduce to, some common E prime. All right, so what this means is that diverging paths of computation, whenever you rewrite, always manage to come back together, hyphenated most of the time as well. So the Church-Rosser theorem. One of the most interesting consequences of the Church-Rosser theorem is just the fact that every term that's fully evaluated down to weak head normal form is unique up to alpha equivalence. Now, why is that? Well, think about it like this. Every term that's in weak head normal form can't have any more computational progress made under it. That's just one rule we've imposed. We never evaluate under lambdas. So assume that you have some other reduction sequence that gets you to some other term. Either that term can take a step and keep reducing, or it will reduce in some normal form. Let's say that that normal form is different than this term. Well, that would violate the Church-Rosser theorem, because the Church-Rosser theorem says that every term has to be able to step to some common term, right? So if you're done reducing, you can't reduce anymore. You have to be at this unique term that you've evaluated to. All right, so let's do some practice problems. This problem says to give the call by name and call by value reduction sequence. So it's asking us to reduce this expression right here using both call by name and call by value. All right, so using the call by name approach, we're going to perform this application, and we're going to take this body, we're going to substitute this argument right here, and we're going to just get this argument. So we're going to get lambda y, lambda y. Now there's only one possible beta reduction to perform, so we get this final answer. Now on the other hand, in the call by value interpretation, we're always going to try to reduce values down to, arguments down to values before actually performing applications. So when we reduce this argument right here down to its value, lambda yy, now we'll be ready to perform this final application and get our result lambda yy. All right, now this next problem is asking us up to alpha equivalence, evaluate this term using both call by name and call by value reduction. Well, we should see something pretty fast, which is that we've got the omega combinator in here. So we know something fishy with non-termination is going to happen. So let's try the call by name evaluation strategy. So using call by name, we are essentially just going to throw this argument away. We'll perform this application right here because, of course, it's the leftmost application. And we'll get our answer back of lambda yy. And then we're at a weak head normal form because, of course, we can't make any progress to further evaluate a lambda. All right, but the call by value reduction instead is always going to try to reduce an argument down to a value. Unfortunately, when you try to do that, you're going to be able to continue to do it forever and ever and ever, all right? Because you can always continue reducing this argument right here down to a value. So just to wrap up this lecture, I'm going to mention that if a term does have some normal form, that normal form can definitely be found by using normal order or lazy reduction. So if we use call by name, normal order, or usually what's called lazy evaluation, we'll always do the least amount of work and we'll always be most permissive in terms of being able to find answers to expressions, assuming that they do terminate. Using the call by value reduction strategy, we're going to do the most amount of work in terms of evaluating computation that might lead us to non-termination. And so if an expression does have some normal form that can be found, it's going to be able to be found by using call by name. If it has a call by name interpretation, it does not necessarily have a call by value interpretation. But if we can reduce by call by value, we must also be able to reduce by call by name. Now, in some ways, call by value and call by name seem like kind of academic concepts, but they do end up being somewhat useful, at least in the sense that it's worth knowing that lazy programming languages exist, because especially as you typically program in eager or call by value programming languages. It's kind of nice to be able to think about what the call by name semantics might give you. And over the next few weeks, we'll think about what could happen if we take a call by name interpretation some of the time. It's kind of cool to see the results, and I'll try to point them out as we go through the class. So all right, see you next week when we'll be talking about church encoding, one of my favorite topics in all of computer science. I'm really excited about these lectures, so I'll see you there.